The next problem is probably the hardest one you're gonna see in this course. It looks fairly innocent, so consider a hotel with infinitely many rooms, arranged sequentially. So a single floor and a big corridor, one room after the other, on a single floor. The rooms are labeled by integers I and z. Room I minus 1 is left of room I plus 1 is right of room I. A finite number of violinists are staying in the hotel. No two violinists are in the same room, so no roommates. So here is an example. I'm gonna mess around with this example a bit more afterwards. But so, of course, I cannot draw an infinite hotel, but I can draw a finite part of it. And since there is only finitely many violinists, there is a finite part that fits them all. So here is, for example, 5 violinists. Every cell is a room. So this room has 1 violinist, this room has 1 violinist, this room is unoccupied, and so on. Each night, some 2 violinists staying in adjacent rooms move apart. They discover they're noisy, and so they want to move apart to have more space between them. One goes into the nearest unoccupied room to the left. The other goes into the nearest unoccupied room to the right. So only one pair of violinists move each night. So there is no simultaneous moves. So let me show how this acts out on this example. So on the first night, either this pair move apart or this pair move apart. Let's just look at what happens if this pair moves apart. So 1 and 2 move apart. One goes to the nearest unoccupied room on the left, and the other goes into the nearest unoccupied room on the right. So let's say 1, the first one moves left, and the second one moves right. Now we still have noisy neighbors. So these 2 pairs want to move apart, these 2 pairs want to move apart. Let's say that this pair is the first one to move apart. So on the next day, 2 has moved left and 3 has moved right. And moving right in this case means jumping over 4 because it goes into the nearest unoccupied room on the right. Now we have 2 more pairs that need to move apart. So let's move these 2 apart in the next night. 3 and 5 moving apart. One goes left, which is, let's say, 3, and one goes right, the 5. Actually, the identities of the violinists don't really matter, so I could just as well put asterisks instead of the numbers. Now we still have 2 violinists that ought to move apart, 3 and 4. So let them do it. 3 goes left. Oops. Sorry, I need to repeat it. 3 goes left, 4 goes right. And another pair, 2 and 3. Next night they move apart. 2 goes here, 3 goes here. And 1 and 2 still need to move apart. And now we have arrived at a state where no 2 adjacent rooms are occupied. So nobody can move apart anymore because there are no neighbors. And the claim is that this will always happen. Prove that no matter how they move, no matter who moves first, no matter what the original state is, so where they originally live, the moving will stop after a finite number of days. That is, at some point, there won't be any 2 violinists in adjacent rooms anymore. it kind of feels intuitive because when they're moving apart, they're widening the distance between each other. At some point, they should be distanced. But the problem is, as we have seen here, for example, when they move apart, they can get closer to other violinists. And the hope is somehow that nevertheless they distance each other out, just maybe with some detours. Now, how do we prove this rigorously? So, first of all, we don't care about the identities of the violinists. We only care, so we only need to know which rooms are occupied. So, thus, we identify a state with the set of all occupied rooms in that state. For example, the state we started with, so this state is the set. So I'm going to start counting rooms here. So I'm going to assume that this is the zeroth room. Then this is the first, this is the second, this is the third, this is the fourth, this is the fifth. So the fifth one is occupied. The sixth also occupied. The seventh is free, but the eighth and the ninth are occupied. So I write 8 and 9 here. The 10th is free and the 11th is occupied. So if we assume that the leftmost box we drew corresponds to room 0. So any state is a finite subset of Z. A finite set of rooms. Next, a monovariant. We define the energy of a state S to be the sum over all I in S 2 to the I. So for example, for example, the energy of this state is 2 to the 5 plus 2 to the 6 plus 2 to the 8 plus 2 to the 9 plus 2 to the 11. Sorry, not energy, entropy. So physicists should best not listen to this at all. This has nothing to do with entropy in physics. I'm only calling it an entropy because it's something that's going to increase all the time. Energy would be a bad notion for it because energy is known to stay preserved. But this is just words. So here's my claim. The entropy of a state increases with every move. And when I say move, of course, I mean two violinists moving apart, not just one of them, but both of them. Oh, I should, by the way, I should have said that when two violinists move apart, of course, in theory, one of them could just stay in his original room, but no, this is not how we're defining this moving apart. So we're trying to be fair. None of them gets to stay in their old room, even if it's no longer noisy in there. Okay, and I have to say, if I do this all in detail, this will take an hour. So proof of claim 1, you do it, or see it in the notes. It's a nice little computation. Now, so we have found a monovariant, the entropy. Unfortunately, this is not the whole story. So this is not in itself enough to solve the problem. Why? And so the thing is, in theory, the entropy could keep increasing forever. There are infinitely many finite subsets of Z. So there is, we won't get this kind of argument that we did previously, where at some point it just has to stop increasing because it cannot, there is nowhere to increase anymore. So, and their entropies are unbounded. However, let's not give this idea up. It would be nice if we could somehow show that the set of all reachable states in other words, states we can reach when starting with a given with a given initial state is finite. Indeed, if this is true, then the set of all possible entropies that can be achieved is also finite. And then the entropy could not keep increasing forever. This would then show that the moves have to stop. So this finiteness, if we have proved it, then we can conclude that then the problem will be solved. And this is what we're gonna do. So we will indeed, so this is what we shall do. First, some notations. Let S0 be the initial state, which, as I recall, is a finite subset of Z. Consider a sequence of moves starting with S0, leading to S1, S2, and so on, Sg in this order. So S1 is obtained from S0 by a move, S2 is obtained from S1 by a move, and so on. We shall prove an upper bound on G entirely in terms of S0. What this will give us is we're going to know that we cannot do more than this upper bound many moves, and this means the moves have to stop. So how do we do this? Let n be the total number of violinists. This number, of course, does not change because violinists only move around the hotel. You don't gain or lose any violinists in the process. So all of these states have the size n, because remember, the state is a set of occupied rooms, so the size of the state is the number of occupied rooms, and because there is only one violinist per room, this number of occupied rooms is also the number of violinists, which is n. And of course, we can assume without loss of generality that n is positive, because otherwise there is no violinist and the problem is trivial. So the sets S0, S1, and so on Sg are non-empty, and they're also finite. Hence, they have minima and maxima. Now, we take a look at mean, so at the leftmost occupied room in a state S, and S will be one of the states. So the leftmost occupied room in a state S, this is the room min of S because of how we defined S as a set. How does this room change when two violinists move apart? There is a pretty good answer to this. It turns out that it either stays where it was or shifts one room to the left. It cannot move right, it cannot move left by more than one step. There's only these two options. That is, we have minimum of Si plus 1 is either minimum of Si or minimum of Si minus 1 for each I. Just realizing I don't need all these symbols. Okay, there. And proof of claim 2, again, I leave it to you. The trick is, if you can call it a trick, violinists never jump over unoccupied rooms. If a violinist moves, he might have to jump over occupied rooms, but he doesn't jump over unoccupied rooms. He picks the closest one in his direction. So you should not expect this minimum to go further than necessary in a single move.